Hello everyone, and welcome to a discussion of gravitational potential energy. Before we actually derive an equation for gravitational potential energy, let's remember what we just did with elastic potential energy of springs. So remember, we did a lab in which we found Hooke's law, which said that the force exerted by a spring is equal to the spring constant, the strength of the spring, times its elongation or compression. And it's negative because the force and the elongation are always in opposite directions. If you stretch a spring to the right, it'll pull back to the left. And so this was the equation we had. We graphed it. Graph of force exerted by a spring versus elongation would be down here in the fourth quadrant. And we said, well, as you stretch a spring, you get more and more elastic potential energy stored. So what on this graph gets bigger and bigger as we stretch the spring further and further? And of course, we decided the area under the curve does. So we defined the elastic potential energy as the negative, because this area is under the axis, so we want to turn it into a positive. So the negative of the area under the curve of the graph. And when we actually worked that through for a elongation x, which resulted in a force F sub s, we came up with an equation for this area, this nice triangular area, of 1/2 kx squared. And so that was kind of our thought process. We did a lab to figure out how the force was related to the elongation. We graphed it, we defined something on the graph to be the elastic potential energy, and then we did the math to see what equation we could get. So this is exactly what we're going to do for gravitational potential energy. So consider here a box of mass m lifted from the ground to a height yf by a constant applied force Fa. And watch this again. So there it is. And it's just being lifted up to another height. Now by lifting it, we are of course storing gravitational potential energy. Now that gravitational potential energy is being stored because of the force of gravity. And as long as we're near the surface of the Earth, we know that that force of gravity is constant. An object weighs the same whether it's up here at the top or down here on the floor. And the force of gravity always points downward and is therefore negative. So let's make a graph here, kind of like we did with the spring. We're going to make a graph of force of gravity versus height. Now notice the symbol I'm using here for height. As I did here, I'm using a y. Remember that y stands for vertical position. Some books will actually use a lowercase h for height, but I'm going to use the more technical y, so vertical position. Since the force of gravity is constant, on a graph of force of gravity versus height, that'll make it a horizontal line. Since it's negative, it'll be below the axis. So again, this represents a constant negative force of gravity as a function of height. Now, as we lift something higher and higher, we store more and more and more gravitational potential energy. So we want to define something on the graph that gets bigger and bigger as you lift the box higher and higher. Hopefully you notice what I'm pointing to. Something that gets bigger and bigger as y gets bigger and bigger is again the area under the curve, just like we did with the spring. And just like with the spring, this is a negative amount of area because it's under the y-axis. And therefore, if we want to store positive energy, we have to make it the negative of the area under the curve. So we are going to graphically define the gravitational potential energy, E sub g, to be the negative of the area under the curve of the graph of force of gravity versus height. Now, we don't even have to do a lab to figure out the force of gravity. We've already done that lab. And so we don't have to do a lab like we did to first understand springs, then we could define elastic potential energy. We've already done a lab on the force of gravity, and now we're defining what that's going to look like graphically. So, if we allow something to be lifted to a height y, while the force of gravity is a constant f of g, the area under this curve is simply a rectangle. And of course, you find the area of a rectangle by taking length times width. So as we just defined the area under this curve, the negative of it, to be the gravitational potential energy, this area would be the EG, would be the negative of length times width. Now I don't really care which dimension, which order we do, so this dimension is f of g, and this dimension is y. However, we did a whole lab and we've used many, many times this year, the fact that the force of gravity is the mass times the gravitational field strength. Now, why did I make this negative? Because it's a vector, and the force of gravity always acts downward. So if we're going to substitute for a vector here, we need to make it a vector here. So I'm going to substitute that right in, and we get Eg equals negative of negative mg times y. The negatives cancel, and there's our math model. A nice simple gravitational potential energy is equal to the mass times the gravitational field strength times the height. Remember, mg is the force of gravity, or weight. So Eg is really dependent on how much something weighs and how high it is in the air. Just a simple mgy. No squareds, no square roots, not even a 1/2 like in the EE equation. So this is a nice simple way of figuring out the gravitational potential energy. Units here in this case, well, mass would of course be in kilograms. Gravitational field strength is in newtons per kilogram. And height would be in meters. Notice the kilograms cancel. We're left with Newton meters, and as we defined the other day, Newton meters are joules. So in fact, this equation, as long as we use kilograms, newtons per kilogram, and meters for the height, we will get joules out, joules of energy. Now, what if instead of lifting the box from the ground to a height y, we started it a little bit above the ground, yi, and ended it above the ground even higher at yf? Well, we could do this a couple of ways. First of all, we could just find the area of this rectangle right here. But I want to kind of write this in a calculus-y way for those of you that are there. So we could find the area under the curve from yi to yf, that area, by first finding the area from 0 to yf, that's the big area, and then subtracting off the area from 0 to yi. I know this seems like a more complex procedure, but this is calculus. So let's go over that again. Okay, we could find the area under the curve from yi to yf by taking the area from 0 to yf, that big rectangle, and subtracting off the area from 0 to yi, the little rectangle, and that'll leave us with this rectangle. Now, we don't even have to do the math. We've already done the area of a rectangle on this graph, right? It's mgy. So the area from 0 to yf would simply be mgyf. The area from 0 to yi would be mgyi. And this is final minus initial gravitational potential energy. Of course, because change in means final minus initial. A positive change means you're gaining gravitational potential energy. A negative change means you're losing gravitational potential energy. Remember that energy is a scalar quantity, not a vector. So the positive and the negative doesn't mean direction here. It means you're getting more or less. For those of you not in calculus, you can turn this video off now. You're done. For those of you in calc, of course, we can define the gravitational potential energy if it's the negative area under the curve of the force of gravity versus height graph. In calculus, that is the negative integral of the force of gravity with respect to height evaluated from yi to yf. Plug in f of g, which is negative mg, and you notice the negatives cancel. Well, as long as we're near the surface of the Earth, m and g, mass and gravitational field strength, are constants. So the integral of a constant with respect to height is just the constant times the height. I just use the power rule. Evaluated from yf to yi to yf, you evaluate at the upper limit minus the lower limit. Hopefully here you see the relationship between this process and the graphs that we had on the previous page. Because if you do, you'll understand why they're teaching you integrals in second semester calculus. So I hope you understood and enjoyed this little discussion of gravitational potential energy. From here, we're going to move on into finding other math models with experiments.